Good afternoon, class. We will end this course with a brief discussion on linear regression, which is chapter 12. Linear regression looks at the relationship between different variables. So in our class, we will consider two variables. By knowing how the variables are related, we can make a model that allows us to make predictions regarding the variables. The most common graph used to show the relationship between two quantitative variables is a scatter plot. A scatter plot is a graph on the coordinate plane that contains one point for each pair of data. Let's first recall a few basic ideas from an algebra class. The coordinate plane is just another way to reference our xy plane. So remember that in algebra, our x-axis is our horizontal axis and our y-axis is our vertical axis. And these two axes are perpendicular. All points in the plane are written as ordered pairs. The x value comes first and the y value comes second. When graphing the point 4, 2, for example, in the plane, we first move 4 units along the x-axis, then 2 units along the y-axis. So I would count 1, 2, 3, 4 along the x-axis or the horizontal axis, and then 1, 2 along the vertical axis. And here is my point 4, 2. When constructing a scatter plot, the choice of which variable to put on which axis depends on whether or not we believe that one variable might influence the other. An explanatory variable, or in an algebra class we would call this the independent variable, is the variable whose fluctuation in value influences a change in the value of another variable. These values represent our x values. A response variable, also known in our algebra class as the dependent variable, is the variable that has its value change as a result of a change in the value of the explanatory variable. These values represent our y values. Let's look at an example. So we want to draw a scatter plot for the following paired data. So we have our age in years, and this is going to represent our explanatory variable, or our x-coordinate variable. And we have 34, 43, 49, 51, and 65. And our bone density in milligrams per centimeter squared is going to represent our response variable, or our y variable. And this is a typo. This should have a comma y to let you know that this is our response variable. And the data given for y values are 946, 875, 804, 723, and 691. Now, we first notice that each value x corresponds to a value y in the table. So we can create our ordered pairs x, y. So we have 34, 946, 43, 875, and so forth. And now, when we plot these points, we obtain the following scatter plot. So let's look, for example, if we wanted to plot 34, 946, I would move 34 units along our horizontal axis and 946 units along our vertical axis. So here is the point 34, 946. And you can do this similarly with the other paired data. A few things to note. Our starting values have been shifted on our coordinate axes to account for the data values given in the problem. This is to eliminate blank space. So notice that instead of starting at the origin, as we would do in an algebra class, 0, 0, notice that we've drawn our graph starting at 30, 600, right? And this is because looking at the values, there's no x value below 30, and there's no y value below 600. So we want to shift it so that we don't have a lot of blank space in our scatter plot. Now, the second thing to note is the importance of a scatter plot is that it enables us to identify trends in the data. If the points in the scatter plot roughly follow a straight line pattern, then we say that the two variables appear to have a linear relationship. Notice that the points in our scatter plot of age versus bone density appear to have a linear pattern as shown below, right? We can imagine kind of a line drawn through the data points here. That is, over time, bone density appears to decrease. Notice that our age and year, as we become older, our bone density decreases, right? It goes downward. The following figure demonstrates the difference between a strong linear relationship and a weak linear relationship. So notice that a strong linear relationship, all of the points pretty much lie on the same line. A weak linear relationship, we can imagine a line, a trend, a line going upward through the data. However, not all points lie on that line. Now, if we had something in this scenario, we would say there's no linear relationship. And we also have examples in other classes of nonlinear relationships. Notice that this data looks parabolic here. When points in a scatter plot roughly follow a straight line, the direction of the pattern tells us how the variables respond to each other. A positive slope indicates that as the values of one variable increase, so do the values of the other variable. So notice that, remember from an algebra class, a positive slope goes upward. We can imagine drawing a line. When looking at it from left to right, the line goes up. A negative slope indicates that as the values of one variable increase, the values of the other variable decrease. So notice that again, as we look at it from left to right, so our one variable increases, our x, our y values are decreasing. A simple visual examination of a scatter plot is not a sufficient way to analyze data. The Pearson correlation coefficient, denoted by the Greek letter rho and pronounced rho, is the parameter that measures the strength of the linear relationship between two quantitative variables. This is a population parameter. Remember that in this class, when we use Greek letters, they represent population parameters. The correlation coefficient for a sample is denoted by R. So we're going to mimic that rho. Rho starts with R, so our sample is going to be denoted by R and is given by this following formula. So notice that this value is always between -1 and 1 inclusive. So that is, R can be -1 or +1 or anything in between. Now, this formula looks very frightening, but don't worry, we're going to have tricks to utilize our calculator so that we don't have to use this formula by hand. If R is positive, then the scatter plot has a positive slope, and the variables are said to have a positive linear relationship. Similarly, a negative value of R indicates that the scatter plot has a negative slope, and there is a negative linear relationship. Now, if R equals 0, then no linear relationship exists between the two variables. So we can look at it as a spectrum. If R is 0, we're right in the middle, we have no linear relationship. If R becomes closer to 1, we're going to have a stronger positive linear relationship. If R becomes closer to -1, we're going to have a stronger negative linear relationship. We will always use our calculator to find the value of R. So let's look at an example. Calculate the correlation coefficient for the data relating children's ages and heights from the table below. Now, we have our age in years, denoted by X, and our height in inches, denoted by Y. And we have the following correspondence. Notice for every X, we have a corresponding Y. So we can create that X comma Y ordered pair. And if we wanted to, we could plot this using a scatter plot. And I'll show you how to also do that using our calculator here in a second. Now, to find the sample correlation coefficient, we want to open our graphing calculator or our smartphone app, and we want to click our Stat button. Next, we highlight our Edit feature on our calculator, and we click Edit. So we want to input our X data and our Y data. Now, our X values, we will enter into our column 1, L1, and our corresponding Y values, we will enter into our column L2. So going back to the data, we have 1.0, 29.4. So I'm going to enter 1, 29.4 into our L1 and L2. So for every X, there's a corresponding Y. And we saw this back in chapters 2 and 3 using our frequency distributions, right? But now we're thinking of it as an X data and a Y data. Okay, so now what we want to do is click Second and Mode. This will exit our application and return to our main screen. And then we want to click the Stat button again. However, this time, instead of clicking the Edit, we want to highlight our Calc feature. And when we highlight our Calc feature, we want to select our linreg. This is our linear regression, A plus BX. And it's right here. It's 1, 2, 3, 4, 5, 6, 7 down on our calculator app. And I think on our graphing calculator, it's number 8. So our linreg A plus BX. So click this. And when we do that, we want to tell the command that our X values are coming from L1. So I'm going to put second 1, this is going to create my L1, and then comma, second L2, and this is going to tell the calculator to pull my Y values from L2, and then I'm going to close off the command by closing off the parentheses here. And then I hit enter, and I'm going to get A, B. We're not interested in those quite yet, but we see our value R. So notice that we see the correlation coefficient R is approximately 0.980. And the book suggests that we round to 3 decimal places for this value. Now that we've seen how we can calculate the correlation coefficient R, we want to test the correlation coefficient for significance. Now remember that in chapters 10 and 11, we talked about our methods for hypothesis testing. So once again, we will utilize that 4-step process for the remainder of this section. So we know that the closer the correlation coefficient is to 1 or -1, the stronger the linear relationship between the two variables. But how close is close enough to imply statistical significance? The term statistically significant for the Pearson correlation coefficient indicates that a significant linear relationship that is unlikely to occur by chance exists between the two variables. The book describes a method using table I to list critical values for the Pearson correlation coefficient at particular levels of significance. However, we will use methods from chapter 10 to test the correlation coefficient using hypothesis testing. So do not use table I, since on the quiz and on the exam, we will not be given table I. We want to use our 4-step process. If the linear relationship between two variables in the population is statistically significant, then the population's correlation coefficient, again, remember, denoted by the Greek letter rho, would not equal 0. That is, we can set up our hypothesis test as the following two-tailed test. This is always, for this class, how we're going to set up our hypotheses. Our H naught is going to be that rho equals 0. So our assumption is that there's no correlation between the two quantitative variables. Our claim is that rho does not equal 0. So our claim is going to say that we think there is a correlation between the two variables, right? And this is always going to be a two-tailed test. Remember, different, right? Rho is different from 0. Rho is not equal to, when we use the symbol not equal to, this gives us our two-tailed test. For this particular hypothesis test, our test statistic will be a t-value, and our t-value will be given by the following formula. And this formula is our test statistic given on our exam 6 formula sheet. So t equals r over this square root of 1 minus r squared over n minus 2, where the degrees of freedom is n minus 2. And again, next to this test statistic, we're going to remind you on our exam 6 formula sheet that the degrees of freedom is n minus 2. Now be careful, because we saw in chapters 10 and 11, whenever we used the t statistic, our degrees of freedom was n minus 1. So this is slightly different. So we want to look at our exam 6 formula and remember our degrees of freedom is n minus 2. Since our hypothesis test is a two-tailed test, using the student's t-distribution, we will reject the null hypothesis H naught if the absolute value of t is greater than or equal to t alpha over 2. This is always our decision rule for a hypothesis test in chapter 12, when we're testing the significance of the correlation coefficient. Let's recall the step-by-step process for a hypothesis test. So remember, we first want to state the hypotheses H naught and HA. We next want to compute the value of the test statistic. Then we determine the rejection region, and finally, we use steps 2 and 3 to reach a decision for the problem given. Let's look at an example. Use a hypothesis test to determine if the linear relationship between the number of parking tickets a student receives during a semester and the student's GPA during the same semester is statistically significant at the 0.05 level of significance. Refer to the data presented in the following table. So here we have our number of tickets and our GPA. And they don't note this, but on the quiz and on the exam for our class, I'm always going to remind you which quantitative variable represents our x and which represents our y. In this case, we're going to let the number of tickets represent our x variable, or our explanatory variable, and the student's GPA to represent our y variable, or our response variable. Before performing a hypothesis test, we can begin by looking at a scatter plot of the data to verify that indeed a linear relationship exists between these two variables. We will let the number of tickets be our explanatory variable x, and let the GPA be the response variable y. Now, when we do this, you can pause the video and attempt this on your own. When we plot these, there appears to be a linear pattern to the data values. Therefore, it would be appropriate to use a hypothesis test to determine if that linear relationship is significant. Notice it looks like a negative linear relationship. As the number of tickets increase, our GPA decreases. Now, to create our hypothesis test, we will follow our 4-step process. So step 1, we set up our hypotheses as follows. Remember that for chapter 12, it's always a two-tailed test involving the population parameter rho. And rho is the population Pearson correlation coefficient. So it's always set up as H naught is rho equals 0 and HA is rho not equals 0. This will always be our setup for the problems given in this chapter. Our step 2, we calculate our test statistic by first calculating our correlation coefficient using our calculator. Remember that our t-value had the value r in the formula. So we need to first use our calculator to calculate the value r. So remember, to do so, we click our stat and then we highlight our edit. And I'm going to put all of my x values, in this case, the number of parking tickets, in our first column, column L1, and our y values, in this case, are the student's GPA, in column L2. And now I'm going to click second in mode. This will return me to the home screen. And then I'm going to click stat and highlight the calculate feature. And I'm going to click on the ln reg a plus bx. And remember, I want to tell the command that the first column, L1, represents my x's, so I'm going to click second and the number 1 to input my L1, and then hit my comma, second, and L2. And this tells the calculator that it's pulling my y values from the column L2, and then I'm going to close off my command using the right parenthesis. And now we see that our r value is negative 0.586619, right? And also notice that in our formula, in our t formula for our t statistic, we also have a slot for r squared. And this is actually called the coefficient of determination. And we'll talk about this in a second here, what that means, to calculate our t-values. So notice that for this problem, n equals 15, and that's going to help us find our degrees of freedom. So plugging in our values, so we have our r over the square root of 1 minus r squared over n minus 2, and we get t is approximately negative 2.612. Remember that t-values, we always round to 3 decimals. Okay, so here's the calculation. You can pause the video and look at this calculation and make sure that you're getting the same numeric value as I got. So step 4, what is the conclusion reached? So since, we skipped step 3, sorry. Step 3, we need to create the decision rule. So we use table C. This is a t statistic, so we want to use the student's t distribution. So we use table C, and in the problem, they say our level of significance is alpha equals 0.05. And remember that our degrees of freedom is not n minus 1, but n minus 2. So in this case, 13. Looking in the area in two tails, we see that our t alpha over 2 is 2.160. And so our decision rule is that we reject h naught if the absolute value of t is greater than or equal to our boundary value, 2.160. Now, our conclusion is that since our t statistic was negative 2.612, making that positive, this value is bigger than our boundary value, right? 2.612 is bigger than 2.160. So it satisfies our decision rule, so we reject the null hypothesis H naught. Now, if you have any questions about this section, please email me at my UNA email or post in our Chapter 12 discussion board.